Our final lesson about Laplace transforms involves convolutions. Hopefully by the end of this lesson, you won't find it too convoluted. So let's look at the Laplace transform of little f and little g, which are capital F and capital G. We know that the inverse Laplace transform of capital F plus capital G is the inverse Laplace transform of capital F plus the inverse Laplace transform of capital G, which we can just write as little f plus little g. This is due to the linearity of the inverse Laplace transform. But a natural question that we could ask is the inverse Laplace transform of the product of two functions, capital F and capital G, just equal to the inverse Laplace transform of each of those functions multiplied together, little f and little g? Well, what happens if we just look at an example? Let's do the inverse Laplace transform of 1 over s times 1 over s. That's going to be the inverse Laplace transform of 1 over s squared. Well, the inverse Laplace transform of 1 over s squared is just t. Now let's take the product. Let's do the inverse Laplace transform of 1 over s times the inverse Laplace transform of 1 over s. Well, the inverse Laplace transform of 1 over s is 1, so we get 1 times 1, which is equal to 1. So no, the inverse Laplace transform of capital F times capital G is not little f times little g, as illustrated by this example. But I wonder if there is a sort of product that does have this property. And so I'm going to introduce a new product called the convolution. The convolution is a product of functions. So I'm going to let f and g be functions, and I'm going to define f star g as a function of t to be equal to the integral from 0 to t of f of t minus y times g of y dy. And I'm calling this a product because this way that we combine f and g has similar properties to multiplication. Those properties are, for example, commutativity, the fact that f star g actually equals g star f. This is the same as saying that x times y is the same as y times x. So how do we know that that is true? Well, let's look at f star g. We can look at the integral from 0 to t, then of f of t minus y times g of y dy. And then what I'm going to do is look at a u substitution. I'm going to let u be t minus y, and then du is going to be equal to negative dy. Well, when I do that u substitution, then I get a minus sign in front of the integral, and the integral starts at t, because if I substitute in y equals 0, I get t, and then it ends at 0, because if I substitute in t, then t minus t is 0. I get then f of u times g of, now what is y? Y is t minus u du. Well, then I can write this as the integral from 0 to t by switching the limits with that minus sign of g of t minus u times f of u du. But that is exactly the definition of g star f. Now I realize that the definition was with a y, right? But I can use any variable for the integration, and so in this case I'm going to use u. So f star g equals g star f. Now, there are some other properties, just like multiplication, that this convolution holds. F star g plus h is the same thing as f star g plus f star h. So we can distribute the convolution. We also have associativity. F star G star H is F star G star H. So I can change which two functions that I associate first. In the left-hand side, I'm associating F and G together first, and then I'm doing star H. On the right-hand side, I'm associating G and H together first, and then I'm doing F star that product. Finally, F star 0 or 0 star F, those are both going to be 0. That should be easy to see. Now, I've not given the proof of the distributive property or the associative property, and that's because that is going to be part of your homework for tonight. Okay, so why am I interested in this new product? Well, let's look at the Laplace transform of a convolution. So what happens when we take the Laplace transform of F star G? Well, first of all, note that that's going to be a function of S. And that will be the Laplace transform of the integral from 0 to t of f of t minus y times g of y dy. So note that f star g is a function of t. So I am going to take the Laplace transform of a function of t. Well, this is going to be the integral from 0 to infinity of e to the minus s times t done to the integral from 0 to t of f of t minus y g of y dy dt. So what I really have is a double integral. So looking back at multivariable calculus, this is the integral of e to the minus s. This is the integral from 0 to infinity. And then this is going to be the integral from 0 to t of e to the minus st f of t minus y g of y dy dt. So now what am I supposed to do here? Well, whenever I got stuck in multivariable calculus on a double integral like this, I usually liked to switch the order of integration. And so that's exactly what I'm going to do. So what I'm going to do is I'm going to draw a picture of the domain over which we're integrating. Okay, so what we have here is the integral is going first dy. So think about this as being the y-axis, and this as being the t-axis. Okay, and the integral is going first dy, okay? And dy, or y, is going from 0 to t. So y starts at 0, and goes to t. So that is dy. And then dt is going from 0 to infinity. Okay, so now we have, in the t direction, things are going this way from 0 to infinity. Of course, what we have here is the line y equals t. Okay. So if I want to switch the order of integration, so I'm going to do a double integral of e to the minus st. I'm going to have f of t minus y times g of y. Now I want to go dt dy. Then if I want to switch the order of integration, then the integral, if I'm doing it dt first, is going to go from y to infinity. And then if I'm, so I want you to see that if I'm going from, if I'm doing dt first, then I'm going to start at the line y, and I'm going to go to infinity. Okay, and then y will then go from 0 to infinity. So 0 to infinity. Okay. So that's the way in which we changed the order of integration when we were doing multivariable calculus. Okay. Well, now I've got an integral from 0 to infinity, an integral from y to infinity. But what's really bothering me is this t minus y. So I'm going to get rid of that by doing a u substitution, just like we did before. So I'm going to let u equal t minus y, and then du is going to equal dt. Okay. So this becomes the integral, and the outside integral stays the same. It's from 0 to infinity. But now I'm replacing a t with a u, so this becomes the integral of, notice if u is t minus y, then y minus y gives me a 0, and then infinity minus y gives me just infinity. And then I'm going to have e to the minus s. What is t? T is going to be u plus y. And then I will have f of u times g of y, and then du dy. Okay. The next thing that I'm going to notice is that e to the minus s u plus y is e to the minus su times e to the minus sy. And so what's sitting in the integrand is actually a function of u times a function of y. So I can split this integral up into a product of integrals, the integral from 0 to infinity of e to the minus su, f of u du. And then I have the integral from 0 to infinity of e to the minus sy, g of y dy. Now, hopefully you recognize what's in each one of those parentheses, because I have the Laplace transform of f of t in that first set of parentheses, and then I have the Laplace transform of g of t in that second set of parentheses. So using that fact from multivariable calculus, that essentially if we have the product of a function of the two variables, so a function of u and a function of y, then we can split that double integral up into the product of the two integrals. And then looking at this is actually the Laplace transform of f of u, and this is the Laplace transform of f of, or g of y. But again, for integration, we can use any variable for the integration. We don't have to use u and y, so I'm going to choose to use t. And so the Laplace transform of f star g is the product of the Laplace transforms of f and g, which is kind of a cool fact. Okay, so Laplace transform of f star g is going to be the Laplace transform of f of t times the Laplace transform of g of t. So we can call those capital F of s and capital G of s. So what Laplace transform does is it takes this convolution product, and when you move to the space of functions in Laplace transform space, that product becomes just multiplication. And then the inverse Laplace transform of capital F times capital G, so if you have the product of two functions and you want to take the inverse Laplace transform, you're going to have to do the convolution of F and G. Now, hopefully, if you're one of the math students and you've studied a little bit of algebraic structures, that the word homomorphism is starting to resonate in your mind, because it seems that the Laplace transform is a homomorphism. And you can see how F star G is the product in one space, and then the natural product, just multiplication, is the product in the other space. Now, if that word homomorphism means nothing to you, that's fine. Don't worry about it, but I just wanted to point it out to some of the math students. Okay, so let's do some examples. Okay, so first, I want to find the Laplace transform of f of t, which is the integral of t minus y squared times cosine of 2y dy. Okay, that's just a weird way to write that. F of t is t squared star cosine of 2t. And I want to take the Laplace transform of f of t. So Laplace transform of f of t is going to be the Laplace transform of t squared times the Laplace transform of cosine 2t, using that property that we just proved. Okay, so Laplace transform of t squared, if we looked on our chart, that would be 2 over s cubed. And then the Laplace transform of cosine 2t is s over s squared plus 4. And so if I have to take the Laplace transform of the convolution of two functions, that's quite easy. Now, what if I wanted to find the inverse Laplace transform of capital F of s? And that function is going to be 1 over s to the fourth times s squared plus 1. Well, I know that that's the inverse Laplace transform of 1 over s to the fourth convolution with the inverse Laplace transform of 1 over s squared plus 1. Okay, so that's 1/6 t cubed star sine t. Well, what is that? Well, that's the integral from 0 to t of 1/6 times t minus y cubed sine of y dy. So I found the inverse Laplace transform of capital F without having to do anything like partial fractions. The problem is, though, when you find inverse Laplace transforms this way, they're not always going to come out to something nice. Right now, in my mind, I'm thinking, like, how am I going to possibly do that integral? Maybe it's possible to be done. Maybe I could do integration by parts over and over and over again, but I'm not actually sure. And so some of these integrals that you're going to get out of doing inverse Laplace transforms this way are not going to be nice, okay? But they could be computed numerically. There are techniques to look at these integrals numerically, but we shouldn't expect, just because I'm doing the inverse Laplace transform this way, that it's going to come out to something nice. Okay, so let's finally look at solving a differential equation this way. And so I have y double prime plus 4y prime plus 4y equals g of t, where I haven't specified g of t. And I'm doing that on purpose. I want to find out, what does the solution to this equation look like for all sorts of possible forcing functions g of t? Well, I'm going to take the Laplace transform of y double prime plus 4 times the Laplace transform of y prime plus 4 times the Laplace transform of y. And that's going to equal the Laplace transform of g of t. Okay, so this will be s squared y minus sy of 0 minus y prime of 0 plus 4sy minus 4y of 0. I'm going to actually just write this in parentheses just so that we have it that way. So let me get that right again. So it's 4 times sy minus y of 0. And then I'm going to do plus 4 times y. And then the Laplace transform of g of t, I'm going to call capital G of s. Okay, so I got to fill in some of these initial conditions. Y of 0 is 2. Y prime of 0 is minus 3. Here, y of 0 is 2. And so I'm going to get, let's see, I'm going to get s squared plus 4s plus 4 times y. So those are all the things that are multiplying y. Okay. Then I'm going to get a minus 2s. And then I'm going to get a plus 3. And then I'm going to get minus 4 times 2, which is 8. And that whole thing is going to equal g of s. Okay, so this becomes s squared plus 4s plus 4 times capital Y is going to equal 2s plus 5. If I bring that all the way over to the other side, plus g of s. So y in this case is going to equal 2s plus 5 plus g of s over s squared plus 4s plus 4. So we're going to write that as, I'm going to write this as 2s plus 4 over, now notice our denominator is s plus 2 squared, plus 1 over s plus 2 squared. So notice I divided up the 2s plus 5, so that was 2s plus 4 plus 1. That still gives me 2s plus 5. And then I'm going to put the plus g of s over s plus 2 squared. Now 2s plus 4, maybe I can write that a little bit nicer. Maybe that's 2 times s plus 2, which would be really nice because then, of course, I can cancel the s plus 2. So this one cancels with that one. Well, then, what is little y of t then? So what happens when I take the inverse Laplace transform? Well, the inverse Laplace transform of 2 over s plus 2 is 2 e to the minus 2t plus the inverse Laplace transform of 1 over s plus 2 squared. Okay, so that, remember, looks like 1 over s squared, and I'm translating using an exponential. So the inverse Laplace transform of 1 over s squared is t, but that's going to be multiplied by e to the minus 2t. And then finally, I have a capital G of s divided by s plus 2 squared. So I have capital G of s times 1 over s plus 2 squared. So that's going to be g star t e to the minus 2t. Because capital G of s is being multiplied again by 1 over s plus 2 squared, which we already saw has an inverse Laplace transform of t e to the minus 2t. And that's the solution, no matter what g is, which I think is pretty cool, because what you can see is you can see you have the critically damped piece. That's from the homogeneous solution, right? And then I have a particular solution, right? Something that I might call the transient since the critically damped part is the steady state. And so now if I put in any forcing function g of t, then I can get the solution by computing that convolution. Sometimes that convolution integral will be easy to do. Sometimes it'll be more difficult to do.